Okay, well, good morning to everyone here in New Mexico, and that is west of the Mississippi, and then good afternoon to everyone east of the Mississippi and to our colleagues across the pond. Today we have Monika Kusiak, who is going to be giving us a presentation on understanding the chronological record preserved in zircon. So Monika is a professor at the Department of Polar and Marine Research at the Institute of Geophysics, Polish Academy of Sciences, and head of the Geoprocessing Belsk Laboratory. Her research is concentrated on uranium, thorium, lead geochronology of accessory minerals, with main focus on applying a variety of isotope techniques to understand evolution of ancient rocks, mostly obtained from polar regions, in order to understand the behavior of elements at the nano as well as the microscale. She is particularly interested in early Earth processes. She has also participated in 11 polar expeditions to Antarctica, Greenland, Labrador, and Svalbard, leading 6 of them. In the 2021-2022, she took a part of the expedition to reestablish the Polish Antarctic Station in the Bunger Hills Dąbrowski as the first and still the only Polish female. And so, Monika, we are extremely excited to hear from your talk today, and we are very privileged to have you today. So please, without further ado, take it away.
Hello, everyone. I have to say I feel really very honored to give this talk, but as well a little bit stressed because I'm not a specialist from extraterrestrial samples. So some of the results from my talk will be, the talk will be kind of three-parted strategy. I will tell you a few words about Antarctic samples, then zircons from Jack Hills, and then something from lunar samples at the end. And it will be more like showing some observation with not yet conclusions. So yeah, as I mentioned, it will be about zircons. So we all know it's zirconium silicate. It's probably the most robust uranium-lead geochronometer, and we actually date various processes with the zircon. And first, about Antarctic zircon, because this is where is my most experience, and as well when I find out I think still the most interesting feature, or maybe not the most, but very first time really interesting feature in zircon. So this was in the Napier complex in East Antarctica, where we have the information that grains as old as 4 billion years old occur. And we know that this is the part where 2 metamorphic events as well occurred 2.8 and 2.5 billion years ago. And one of these events was as high as 1100 degrees Celsius, which is ultra high temperature metamorphism. And when I got the samples to analysis from the 3 areas, which are marked here on this Google Earth, it's a Gate Ridge, Mount Sons, and Dulwich Nunatak. Already those samples were dated by starting with work by Ian Williams, then Lance Black, Simon Halley, Chris Carson, and Nigel Kelly. And all of them noticed that those grains, which are the oldest, so that from perspective of working on early Earth processes, the most interesting grains were reversely discordant. And as well, believe it or not, whenever we read the paper and data interpretation, age interpretation, when we have discordant data, we can quite easily, or maybe not quite easily, interpret it, because the interpretation is that it's either the mixing of various zones, older and younger, or it's just open system behavior. So we have some fluids or some other things, or lead loss. Lead loss is kind of very common process in zircon, as we know. But with this very first study, when this was reversely discordant data, Ian Williams suggested that maybe we have process like lead gain, opposite to lead loss, which was not really so popular. So many of these data were not really interpreted. They were provided, but with no really interpretation. And when I got my first results which were done in Stockholm with Martin Whitehouse, you can see what a mess. Those of you who work with zircon can see, it's impossible really to determine the age from this sample. And despite of the thorium uranium content or just uranium content, we had reversely discordant data. And here I would like you to take a look on this diagram on the left. I'm not sure if you can see my mouse, but take a look on this axis where we have ratio 7:6 ratio. Ellipses are slightly elongated. And this took us to have a very first thought, oh, maybe something is wrong with lead in these zircons. As we know, lead is not incorporated into the zircon structure, and we assume, I mean, it's the basic tenet of uranium-lead geochronology, that the lead is radiogenic effect of uranium or thorium decay. So we took a look into the individual analysis, and really lead was not behaving homogeneously. So choose few grains. As you can see in the top row, these are cathodoluminescence images. So this brightest one has exactly 123 ppm of uranium, and these dark zircons have more than 1000 ppm of uranium. And these squares inside the area, these are 70 by 70 micrometers square, where we did ion imaging mapping of the area, which was previously dated by the SIMS spot. So in the middle of each grain, you have the spot, which was analysis, which the 7:6H given, and then you have the mapping. And I mean, really was shocking, because if you see on this map, we have this, I don't know, we call it goosey spots of lead. I mean, lead is not behaving in the maps as it was supposed. We thought it will be kind of more or less homogeneously distributed. And you can see as well, it's despite of the low and high lead content. We double check again common lead maps, so we can see like signal means that it was no lead in this zircon. So we do not have kind of problem with common lead. Hafnium imaging are very uniform, as we expected. These slightly bright spots, which you can see here, they are again spots after the SIMS spot where the uranium lead analysis was done. If we took yttrium zonation, we know yttrium is one of the content of yttrium is visible on the CL images, and here was very nicely no surprises with yttrium content. And then uranium content it resembles us yttrium. And at the end, one more surprise. Look at the titanium. Titanium is again spotty or heterogeneously distributed. And again, it kind of, I mean, resembles uranium, but not always. It doesn't really always correlate with uranium. Not uranium, with lead content. So we immediately find out that, for zircon, which are our basic minerals for uranium lead dating, there is some issues with lead. And on top of this, that as we know, we use titanium in zircon for titanium thermometry. And again, we have some problems here. And this was my Marie Curie project, with later on developing the Humboldt project. So I started to work on this problem. Titanium was I never really focused that much, because still lead problem is not resolved. But I would like just to show you only the example, which were done on the synchrotron, that if titanium is in the cracks, we can see how it is in the cracks. If it's inclusion, we can see how these are inclusion. But this distribution is really, really heterogeneous distribution of titanium. And as well, using the nano SIMS, we made kind of 3D mapping to see how it is this. So we can see that next to the titanium and lead, we had as well aluminum in this zircon. One thing which was really kind of dangerous and scary, that when we did that simultaneously maps of 207 and 206 lead, and as we know in uranium lead geochronology, we use this ratio for calculating the age. We could, using the wind image tools, we could really make the various area of zircon to determine the age. And in these squares, which are again 70 by 70 micrometer size, we could find out that we had 3.8 up to 4.2 kind of zones or clusters or circles or hotspots of ages. But of course, this was false ages, not ages, but some data. So what we did took these grains for TEM analysis, and most of my talk now, since now, will be to show you TEM results. As you can see, so here we have area which was ion imaged, and then on this colorful ion imaged area, the tiny square, it is the square which was under the transmission electron microscopy, and here you can see which was striking the white circles of what later was pure lead. Here we have the scale of 150 nanometers, and then at the bottom line we have lead, titanium, aluminum, and zircon, which shows that with the elevation of lead and titanium and aluminum, we have depletion in the zirconium content in zircon. So we knew immediately that we deal with some cluster of leads, and they are confirmed by on the EDS. And as well, in this particular case, which was very interesting, next to the lead sphere, we have titanium aluminum kind of cluster or some kind of, because it was not having mineral phase. And all of this is in the black, which is silica point. And these features are in mineral zircon, zirconium silicate. So when we analyze those grains, I have to tell you that we were really shocked when we find out that lead is in a pure metal lead state. So we had no lead silicate, not lead oxide, or not lead sulfate. I mean, having so much of the oxygen and silica in the area, it was pure lead in the zircon, and sometimes this lead was completely alone, metal lead nanosphere in zircon, and sometimes it had clustered, or sometimes it had tiny droplets of lead. Here is the in the middle of the image is the example where we have lead with the silica. And here, this is the confirmation. We have angles and length of vectors, which confirmed that this was pure metal lead. So later on, after this study, there were a few studies. They were, of course, studied on Jack Hill's zircons in Western Australia, the oldest terrestrial grains on Earth. And this was work, I mean, here it is the image from the paper of Frank von Gey. He did his ion imaging as well with Martin Whitehouse. And you can see here various spots on ion imaging showing that we have more lead than in one areas than in other. And of course, now we can see easily that if we put our, and I mean, this is the scale which is invisible on cathodoluminescence normal image, which we have documentation usually before dating. So if you take a same spot on the area with elevation of lead, we go to reverse discordant data. If we have elevation, of course, we need to have depletion of lead. So then we have discordant data. So I had a chance to take grains from Bob Pigeon, from publication, which was Bob Pigeon with Sasha Nemchin and Martin Whitehouse. They did very careful study of hundreds of zircon grains from Jack Hills, which they divided by 5 groups, starting group number 1, which was pristine 9, very concordant grains, and then going to group number 2, 3, 4, 5, with group 5 being usually either discordant grains or with OH high or low. So for my study, I choose the grains which were concordant, discordant, and reversely discordant. So whenever you have D is discordant data, whenever you have RD, it's reversely discordant, and C is concordant data. As well, I choose grains with low and high uranium content, and as well with various delta oxygen and OH content. And this was like very careful study, and I have to tell you that they find out lead nanospheres in Jack Hills zircons with no really correlation or no possible correlation which we found to either uranium content or to oxygen content or OH content. We find them in concordant, discordant, and reversely discordant data. And the only thing is that we didn't find them in grains which were younger, which were 3.3 grains, and we didn't find them in grains from group 1. So this the most pristine and very nice grains. So that this is still the work which is going on, and this is still what we find out, that these grains had various cracks, and that we find out that lead nanospheres were present despite of the cracks. So they are not connected with any fluid infiltrations or cracks. So this is a feature which is in zircon grains by itself. And I would like to show you what the implication of this finding is. And here we have the 3 examples, like model examples, red, blue, and green one, with crystallization age and possible metamorphic age. And if we take a look into the example red one, if we would have zircons like in Antarctica, 3.6 or something million years old, with metamorphism 2.5, we immediately see something's wrong with our grains, and we immediately see that reversely discordant data are an indicator of some strange process. But if we have grains which are 4 billion years old, with some metamorphic events 3.8, then we would need the data being at least 4.2 billion years old to realize that we have issues with our analysis. So we can't see analysis for like plus minus 200 million years old that we have not pristine nice grains. And finally, the last example, an example which is might be important for working with really ancient grains from extraterrestrial sample, is that if we have 4.2 crystallization age with some kind of issue at 4 billion age old, then you need data exceeding 4.4 GA to really understand that something is going on. So I had a chance to take a look in some zircon from lunar breccia. This was when I was Humboldt in Geoforschungszentrum, and Dennis Vardelnik, who worked with Harry Becker, he got some data of 3 samples. As you can see, very uniform ages, 4.2 billion years old, 4.2, 1, 11, and 25. And these grains really, I mean, they are very uniform. There is not very big spread of ages. However, because some data were reversely discordant, I asked, if we could take a look into TM with, I don't know if word hope is good one, but with kind of hope to find out lead nanospheres in these zircons. And here I would like to show you more like, I don't know, catalog maybe, the future we find, or how the zircons looked like. But I have to tell you, we didn't find lead zircon here. So lead nanospheres in zircons here. And unfortunately, not all the grains which we had were grains which were dated, because sometimes grains are very, very young. And here in this sample 15455, we have two types of zircon. We had granular zircon aggregate, this one at the top, and we had two grains where zircon was a rim around the badellite, and all these were in anorthite matrix. And this here, the yellow lines, these are lines where the FIP foils were cut for TEM studies. So these tiny areas across the zircon were cut. In the second sample, 67955, we had two subhedral grains, but take a look, they are tiny really. This scale on the left one is 2 micrometers, and the scale on the right grain is 3 micrometers. And actually, both of these grains were dated. And take a look here, because we can see kind of granular phases as well. This is a little bit different feature. In the previous grain, we have granules which were consolidated together. Here, these are granules all together in zircons. And the third sample, 67915, we have the only one idiomorphic zircon grain, this triangular shape. Here we have the spots after uranium lead analysis, SIMS data. And we have as well these aggregates of zircon granules. On the right zircon, this is the leftover after as well uranium lead data. As you can see, these granules are in anorthite, and as well piece of clinopyroxene is visible here. So this is the image which put together all our morphology of zircon. In the top row, despite of sample where they come from, and I'm going to treat them like now by features, not by the specimens, especially that all data were 4.2. They were very, very uniform. But we can see that the zircon doesn't look uniform. We have at the top row idiomorphic and subhedral zircon grains, then granular granules, and then this zircon, which is rim around zirconia, and then all of this in anorthite. So very fast future. This is planar fractures, which, as you can see, are associated with displacement, with visible in crystal grain surface. On this zircon on the left, you have zircon and anorthite, and the tiny, not tiny, the square which marked there is enlarged on the right side, where you can see really very nicely visible planar features. And as well, so this we most likely these are results of the high shear stress during the unloading of a shock wave. Many grains showed our granular textures. With this texture, we had either zirconium oxide inclusions or not. So sometimes they were not present. And as you can see, we have various phases: zircon, anorthite, badellite, and clinopyroxene, which are present here. And as well, we have amorphous phase of zirconium silicate present in this granular texture of zircons. And as well, in the triple junction, which are visible interfaces between these zircon granules, sometimes we could have the filling with silica melt, and this silica melt sometimes contained the spherical enclosures of epoxy. And yeah, this kind of granular shock-related decomposition, and this shows that decomposition and recrystallization of zircon had to occur in a very high temperature and probably above 2715, which is the melting point of zirconium oxide. On this picture on the right, we as well have mosaic zircon and amorphous zircon. I'd like you to take a look on this later on. I will be showing you more in detail this mosaic feature, characteristics of mosaic feature, because it's really very interesting here. Zircon as well, we can see the columnar zircon rims around the badellite. And you can see on the left image, this twin lamellae in badellite with a very few patches of zircon interground, these grayish, more uniform patches, they are zircon on the left image. And as well on this image, we can see columns of zircon, and square B showed the image on the right where we have this columnar zircon rims, and these were formed as a result of the shock-induced local melting of this silica-rich phase, which is surrounding phase around the zircon. And zirconium oxide, which probably is one of the most interesting discovery which was found during the analysis of these grains, because in these samples we have not only monoclinic badellite, and sometimes we call, I mean, at the beginning, whenever we saw zirconium oxide, we called it badellite, but then we find out that we have cubic zirconium oxide, and then not badellite is monoclinic, cubic, tetragonal zirconium oxide, and then cubic zirconium oxide. So 3 forms of zirconium oxide occur in these samples. However, these droplets, and these are very nicely visible on this picture in the center. So these are droplets which are about like 20-30 nanometers in scale. So they are not like huge droplets of zirconium, of cubic zirconium oxide. As well, big porosity and another inclusions, other inclusions in the zircon. So the other inclusions, they are rutile, which is here on the left. This particular rutile grain is in badellite, and as well we have sulfates of iron and iron nickel usually they are in the triple junction in between the zircon crystals. And the last example, this is the mosaic crystal that I choose the most complicated example to show you and to see how really interesting it is, because the very crystallinity is with the zone axis orientation, with the same zone axis orientation. So we have various crystallinity, but the same orientation, which means we deal here with the single crystal. And take a look, starting from the center, number 4 here. We have here the very sharp diffraction spot of mosaic part of zircon, and they are with the same orientation. And then going to the right, to the 5th square here, we can see now that the diffraction spots become to be more fuzzier and broader, and as well they we can see that they are that the rings are more diffusive, and we think that these parts, these recrystallized parts of the zircon, they was growing on the expense of the mosaic crystal, and then finally partially replaced it. And now if we go to the first of the left example, where we have this broad and diffuse diffraction spots, which this in the background we can see the strong diffuse scattering intensity. So this, well, we know we deal here with amorphous material, and then we go to the second and third more slightly crystallinic material. But here what we notice, this slightly sharper the spots and less diffuse scattering intensity from amorphous material, it indicates a crystallization of the nanocrystal of zircons. So here is very nice example where we have in this process of crystallization of nanocrystals of zircon inside the really big single crystal. So amorphous material formed by shock-induced composition on formation of glass that form as a result of high shock pressure, and recrystallized domains are evidence of annealing that in lunar crust could have been caused by heating from subsequent impact events. So now I'd like just to summarize of our observation. We had anhedral grains with planar features, which are likely the results of high shear stresses during unloading of shock waves. We had thick columnar or granular zircon rings around baudolite, and again it was shock-induced local melting of the silica-rich surrounding phase. And granular textured zircon result from shock-related melting and recrystallization of zircon at temperature above melting point of zirconium oxide to 715 degrees of Celsius. So this is the temperature of cubic zirconium oxide. And as well, these granules which contain monoclinic, tetragonal, and cubic zircon as well, these rutile inclusions. So this is effect of rapid crystallization. And the amorphous material, which again formed by shock-induced decomposition of zircon, or possibly as well formation of diaplectic glass, this again is result of high shock pressure, and there is recrystallized domains in zircon. This is evidence of annealing that the lunar crust could have had caused by heating from subsequent impact events. Well, absence of lead nanospheres, yeah, this probably it's indicated of more prolonged exposure to high temperature, and maybe, I mean, we just guessed that it could lead to complete evaporation of radiogenic lead that accumulated in zircon minerals. However, it is really not clear which phases might have evaporated, if it was like metal or sulfides or silica-rich glass. And just the conclusion, so it's was quite surprising to see so many texture in the zircon phases with such uniform 7-6 lead latages and uranium latages, which was for us really very surprising because didn't expect this. So the conclusion is that either shock events occur very soon after the solidification or recrystallization of these different zirconium phases, or it was these shock events were too brief to result in noticeable lead loss during shock metamorphism. Thank you for your attention.
Thank you so much, Monika. So we'll go ahead and open the floor up to questions regarding the presentation. So we'll go with online first, and then we'll get in person. So if you also necessary, you can type it in the chat as well. Yeah, go ahead, Connor.
I was wondering where the lead blobs were coming from. Maybe you said, and I spaced it.
So that we assume that there was no open system behavior. So lead is from the radioactive decay, and now the mobilization could be, so it's the only lead which comes from uranium and thorium. And then probably during the radioactive decay, when the crystallographic lattice of zircon is metamixed, this is the area where lead could be mobilized. However, with the annealing process, where, I don't know, islands of crystallinity grew, then the lead is trapped. And this is how it is still kept, because when the lattice is crystalline, there is no way the lead could be mobilized or moved away. So it's only moved whenever we have puffs of crystallinity, either at the grain's boundary, by diffusion possibly, but I think that the highest chance is whenever it goes, zirconium silicate goes into the amorphic state, when we have puffs of lead mobility, and then among these puffs we have these islands of crystallinity where lead cannot enter. However, later on, if these tiny islands grew and close or trapped of kind of fossilized the lead nanosphere, then we have still process of uranium and thorium decay going on. So it is possible that we have at least two events, 276 ratio of lead in the area of the droplet of this lead nanosphere and of this zirconium crystalline lattice. And we tried this exercise with nanosims to measure 76H only the largest lead nanospheres, and it was more or less with UHT metamorphism even 2.5 in this Antarctic zircon. So still, the mechanism of how this lead is formed in zircon is not really known. It's something to work on still, but for sure, this is not external lead. It's still coming from only whatever is going on inside the mineral zircon, crystal zircon. I'm not sure if I answer your question.
Go ahead, Lars.
That's really interesting talk, kind of frightening. My question has to do with the reversely discordant spots that you had. How do you explain these? If the spherules potentially can be, you could lose the lead as a result of volatilization by impact or something, that of course will get you a normally discordant lead. But how do you get those points above the Concordia plot?
The only explanation I can think of now is that this lead, when it's mobilized, is mobilized in a non-homogeneous way. It mobilizes in the way which is kind of irregular. So we find the, let's call it, hotspots of accumulation of lead, and then we date. And then when we put our SIM spot on them, it is we have more lead than it would be from normal uranium lead decay. Then it is older than it was be. So we have reversely discordant, and then when we, obviously in another area there must be kind of depletion of this lead. But it is why it is discordant. I think it's kind of scary future, and I think probably would be good to maybe to work on find out some physical ideally numbers when we deal with lead which is too much and which is not real, and when is this threshold. Because on Jekyll zircons we showed that it can be that uranium content, I'm not sure if I can say it doesn't matter, but we didn't find any correlation with uranium content. We have grains with 59 ppm of uranium and grains with more than 1000 ppm of uranium. And we showed that we might have this problem. However, some of these grains, they are concordant. So the question is if they, so probably now would be the time either to physically measure, I mean, just calculate and measure how much lead is needed to make our data spurious, or go to the lab and do experiment with measuring this, probably. But I have to, yes, it is a scary future. And the problem is that during our, let's say, normal documentation, which we do on CL, we do not see these blobs of lead. They are so small that they are invisible. I mean, they are visible in TM, not in SIMS. Oh, yeah, or SEM.
Igor, you're up next.
Yeah, thank you. This is very, very challenging, I assume, to understand the mechanism of the distribution of the different elements. And because this is difficult, because there are some extremely conditions during the creation of the samples. And also, I would like to suggest you that you have to consider also the structure of the material. This is some polycrystalline structure of the material. For example, in ground boundaries, area can be different comparing with height of the ground. Some elements which are very heavy can go to ground boundary, cannot go to the grind. For example, I was working with zirconia oxide, where we found that zirconia oxide can be covered by the glass of silicon oxide. For example, this is if you can find the method where you will be able to tell about the composition in correlation with the structure, ground boundary, some inclusions, mosaic, maybe will be some information easier to understand the mechanism of the crystallization. And I have also the question about the isotope method. Because isotope method, you can measure the ratio between the PB207 to PB206, but you are assuming that the conditions are not changing, yeah, because the exponential decay will not describe, I don't know, the explosion of supernova, the million Celsius temperature, extremely high pressure. This may be some not good correlation. Can be the question that we are not starting from the point which we would like to have on the exponential decay, because maybe we started from different point.
Yes, this is, I mean, two very good points. First one, maybe we can see and start working with zirconium oxide. I don't know any TM work or nanostructure work of zirconium oxide. This is something what we now plan with Justin to do. So maybe this will be showing us some future with zirconium silicate doesn't show us, and then we can maybe find out what is going on exactly at the grain boundary and how this lead is mobilized. But about the uranium lead geochronology, so it is why the zircon is this our ideal mineral, and zircon is we dated because it is probably the most robust now mineral for any future, and we assume that there are two assumptions actually during uranium lead geochronology. One is that we assume that the system was closed, so there was not really open system behavior, and then another is that the entire lead which we deal is the result of the decay. So we didn't have any initial lead at the very beginning. And I know this works very well for lunar and Martian sample for dating. However, we still have some results which are difficult to interpret, and I think they are worth of kind of careful attention and taking a careful look in those. Yeah, but maybe some more experiments would be would be not a bad idea.
Thank you. Connor, do you have another question for us?
Hi, hi Monica, it's Carolyn Crow. I have my whole research group here using my students' computers. So I just wanted to follow up on something that Igor said and going to address Lars's question about the reverse discordance. And I think the structure is a really big issue here. Like your TM slices are beautiful, and you can see in there's a whole range of structures from crystalline to amorphous, zircon to cubic badleite to badleite, all within the scale of a typical SIMS spot. And SIMS is very sensitive to matrix effects. So if you have a matrix mismatch between your standard and your sample, you get reverse discordance. And this is very common with metamixed zircons. So zircons where the structure has been damaged, those tend to go towards reverse discordance. We've been doing work too measuring cubic badleites, and they tend to be reversely discordant when we use crystalline normal badleite standards. So I think one of the things your research is highlighting is that some of these grains, especially the shock grains, are very heterogeneous on the scale of or at a smaller scale than the SIM spot, and that's really hard to standardize out and might be influencing the reversely discordant analyses. So, but this is really great talk. Thank you.
If I can interject.
Yeah, I mean, if I can add to, because reversely discordant feature in zircon might be as well as so-called matrix effect, which we could see especially in the high uranium content grains. And this is something as well what is visible. But however, if it is kind of artificial, I think nowadays we can recognize it more. It's not that difficult. And as well, I think whenever we have reversely discordant data, it's worth to take a look into the individual analysis and how this analysis were during the course of the cycle, because then we see abnormal behavior quite easily. So this is something.
Yeah, I agree. I think you need to look at both, right? Like there are multiple things that can be influencing the reverse discordance, and doing this kind of joint approach of understanding the nanospherals and where everything is, and in addition to what is the actual matrix of the sample that you're measuring is helpful for understanding that. Yeah.
If I can interject really quickly.
Yeah, Lars, Thomas, if you have an interjection, go ahead.
We've measured, zircons by TIMS ID that aren't matrix effects, and some of them are also reversely discordant on the same rocks.
Yeah. In that case, I would assume that there was I'm not sure really how to explain it, because we would need to have more lead than it would be normally from radioactive decay. So maybe, I'm not sure, before TIMS, did you do some chemical abrasion of grains or something to get rid of any metamixed parts of the grains?
Yeah,
Lars,
we
if I
use
may
a
ask?
pretty standard approach for that.
Yeah, okay, yeah, so. Yeah, probably, I mean, yeah, this is the I think the lead behavior in zircon, and as well in other minerals, the same as Caroline said in badellite or whatever. I'm not sure if the cubic zirconium oxide is badellite. I think only monoclinic we can call this, or others are zirconia. But that's a nomenclature. But the thing is, anyways, this is still study of lead behavior in this zirconium bearing minerals. And not only in zirconium bearing, because I know Almagali Seydou-Julien was the one who found out the lead nanosphere in monazites. But in monazites, which is light rare element phosphate, actually lead can be incorporated into the crystallographic lattice. But it's monoclinic as zirconium oxide, so it's as badellite. So it might be as well worth to look for the wider variety of accessory minerals which we use commonly for dating, and really I would say lead problem or not problem, that's interesting feature, is something to take a closer look.
Well, thank you, Carolyn, Lars, and Thomas. And so, Justin, I promise we did not forget about you, but Justin, you're up next.
It's surprise, Monica. It's Roy. It's actually not Justin. Love to talk. I'd love to talk, of course, on your mosaic crystals, on those zircons. I understand what you were saying. Basic technical question: those diffraction patterns, are those true selected area diffraction patterns, or are they FFT diffraction patterns?
They were FFT diffraction patterns.
Oh, okay. We'll talk about that.
Tell you, yeah, I have to tell you that I dream of working with you on this subject.
Well, I don't know how to react to such a high compliment, but yeah, let's talk about that, because you know, every time you do an FFT, there's artifacts from what's going on in terms of the vicissitudes of imaging, the lattice fringe imaging at where you're taking it. So I'd like to see the actual lattice fringe images of those areas. Do you have them? You must, if you did an FFT.
Yeah. I have the complete documentation here with me, just for the purpose of showing it to you, actually.
Okay.
So I really hope we can we will be able to go through those data, but as well to really kind of have a appropriate approach, good approach for our new data. So
yeah. All right. So I get another one, and then as Carolyn, I think, mentioned metamix zircons, but there's also been work done on in situ ionomorphization of zircons. And I'm willing to bet they see the same microstructures. Let's go back and check the papers.
Okay, I'll need to double check, because I'm not sure which paper you're talking about.
Let's talk about it online, give somebody else a chance to go. I mean, I'll be seeing you, so you're here.
Mm-hmm. Yeah. I will be tomorrow at the institute. Yeah, now I work with her. But yes, as I mentioned, you're right. I really hope I can get Igor attracted to, and maybe we could do
okay.
some
experiments. It's all wonderful.
Well
Flattery will get you everywhere, even time on the TEM. So.
He's gushing, Monica. He's gushing.
No, I'm
He's
blushing.
Blushing.
I'm blushing.
Blushing is the word.
Don't confuse her.
Sorry.
All right.
Well, thank you so much. I know we are out of time at this moment, but Monica, thank you again for your talk today and stuff. So before we go, I do need to make another quick announcement. So next week we will not have the seminar. It is Thanksgiving here in the United States, so we will have next Wednesday off, and then following that we will have the final seminar of the semester, and that'll be Ryan Ziegler. So everyone have a safe Thanksgiving for those of us in the States. Monica, again, thank you so much. That was a fantastic talk, and we will see everybody again in 2 weeks.
Thank you very much.